Chapter 9, Non-Parametrics. We have almost finished this book. Only one more chapter remaining after this, so thanks for staying together. So let's find out, what does this non-parametrics mean? So a given machine learning model can be parametric or non-parametric. So we have seen a lot of parametric models up until this chapter. And in a sense, parametric models are those that require certain assumptions going into that model specification. Like if you have certain business knowledge about how the systems, what is the causal link between certain things, or what are the variables that are important. And if you have certain assumptions going into building a model, then those are parametric models, because those input variables, those assumptions, those parameters would be given, meaning you will factor them in, and you will make your model learn from the data. And basically you are, by learning from the data, you are adjusting weights or on those parameters. Yeah. So far this makes sense. If none of this makes sense, I highly encourage you to go through the first 8 chapters of this book. But in a sense, what you do is you start off with certain parameters, certain input variables that predict certain output, certain x's that predict y, and then the whole modeling process is about putting weights to those variables, x variables. Yeah, so there will be certain variables that predicts output. And going in, you already assume with a very strong assumption that says, hey, these variables are most likely causing or are responsible for the prediction, right? So those are parametric models. So now we're going to go away from them and find out if there is a way in which we don't go in with a strong assumption that says, hey, x causes y, or x is responsible for y, or x plus x1 plus x2 causes y, right? So that's where non-parametrics come in. We make fewer assumptions as to what are those parameters. We make no assumptions going in, right? We just say, hey, we are going to learn these parameters as to what parameters are actually important. What is it, x, x1, x2 that's important, or it's x, x3, x4 is important? You don't make those assumptions. You learn from the data. So that's this whole chapter about, like, hey, is there a way in which you could build a machine learning model without making too many assumptions going in? And that's the non-parametric model. And so more the data that we have, the better it is for the non-parametrics. So hopefully you get the high level of what this chapter is about. Now there's going to be lots of algorithms that we will go into this chapter. So specifically, there are 4 new algorithms that we will learn. We will learn about decision trees and a specific algorithm called CART, classification and regression trees, random forests, RF, empirical Bayesian forest, EBF, causal trees, and then we will end with an introduction to semiparametrics, Gaussian processes, and deep neural network as a lead into the last chapter, which is chapter 10. So in a sense, these are ways in which we do non-parametric. We understand how we did parametric so far, and now we're going to do non-parametric. But what you see in common in a lot of this is trees, decision trees, regression trees. And random forests are nothing but combination of trees applied in a very novel way. So forests and trees are like, these are like, what we are focusing a lot in this chapter is the concept of trees, but there are many other mechanisms. So let's take a specific example and get into what is a decision tree, which is an example, a technique. A decision tree is a technique to use non-parametric modeling strategy, right? So let's say a specific example is you want to build a decision tree or build a model using non-parametric mechanism. You have lots of data and you want to build a model that says, hey, is there a high or a low risk of heart disease? That's what you're trying to predict, and you want to build a model for that. So what if you were given something like this? So you see, you are given this model which has a root node, a leaf node, and certain decision nodes in between, right? So green are leaf nodes. They start with a root node. So what if you were just given this kind of a mousetrap, right? This is a tree is kind of a mousetrap. You say, hey, I have this parameter that I learned from the model that says, hey, if age is less than 18, then I'm going to go down this path. But if age is greater, then I'm going to go down this subtree, right? So if age is less than 18 and weight is less than 60, then it's a low risk of heart disease. So based on, what if your model has just learned that, hey, if age and weight has certain thresholds that are below, then there's a low risk. So this is an output. This is a decision tree that's built using an algorithm of non-parametric trees mechanism. So it builds this tree, right? And it tells you like, hey, given anyone else that comes in, you just ask their age, and then you check if they're a smoker, and if they're greater than 30 years of age. If they're a smoker, yeah, there's a high risk. So this tree just gives you simple to understand prediction as to why someone is categorized as high risk, and it tells you these nodes. So a decision tree is this. It's an output that tells you where do you start, what's the root node, what's the decision you need to take based on what input you're seeing, and then you get to an output or a prediction. So it's so simple to understand. And it learns how to build this tree using the data. Yeah, so this is pretty powerful. You could imagine several use cases that you could build for your own businesses to predict certain things. And if you have lots of data, you can use decision trees to build that. So you could imagine there are problems with this approach, right? But before we go into that, let's just go one more time a little bit more deep. Now that we understand an example, we understand what parametric, non-parametric is, let's just compare these two as to what are the pros and cons of these two, and then we'll go into the detail as to some more examples and what are the issues with decision trees, right? So we compared briefly at the start of this video parametric versus non-parametric, but in a sense parametric model go in with a strong set of assumptions, right? And no matter how much data you put additional, it won't change its mind in terms of the parameters. It's going to fix that parameter. It's going to change the weights to that parameter. And so we've gone through logistic regression in the past videos, right? So that's an example of that. What's the pro? The pro is that it's simple. It's very fast to build, simple in terms of like you can easily say, hey, these are the weights, these are the parameters, and it's super quick to build. It needs less data. But then you could say the issues are that, hey, it has constraint in terms of like certain parameters that it only looks at those parameters and it's not open to adding new parameters. It has limited complexity, which we will see how it has impact on bias and variance, and it has a poor fit, right? Because it may not be accurately representing all possibilities. Like we saw in this case, you could see that if the age is 18 and 30, it goes here. So all the possibilities are being factored in for these age ranges, right? But so non-parametric is when you have lots of data. So that's the key. That's the key. When do you need a non-parametric MN model? When you have lots of data and you don't want to go in with a lot of decisions upfront in terms of assumptions around parameters. So decision trees are a big one. We'll go through that in this chapter. We'll go through classification, regression trees, random forest, empirical Bayesian forest, and causal trees. But there are many such other techniques for non-parametrics. And you can see the opposite is true, very flexible because they can add lots of new parameters as new data comes in. They're very powerful in terms of baking in those learnings and are super performant in terms of prediction power. But they are super slow in terms of building it, and it takes it overfits because you're gonna encode all the information you have from your data, and it requires lots of data. So that's the high level of like parametric. When should you choose one versus the other? You get a high level trade-offs that you can choose from this one. But in a sense, if you have the number of dimensions that you have has to be less than 1/4 the number of data size that you have. If the dimensions are way higher than the data, non-parametric is a bad way to go. So that's the rule of thumb, simple one, simple heuristic to use. Yeah. Let's take another example to make decision trees really concrete. So should I take an umbrella to work? So that's a simple like decision that we all have to make. Should I take an umbrella to work or not? And you know, we are trying to, in our mind, have this utility function that says, hey, am I okay with the inconvenience of getting wet? Or am I, you know, okay inconvenience of holding this umbrella when there's no possibility of rain? So that's the internal utility function in our head. What if we could build a decision tree that says, hey, check the weather. Is it sunny, cloudy, rainy, right? And if it's cloudy, you know, you want to take the umbrella. But in a sense, there's an input function and there's an output function. And an input is basically a set of parameters that go in to say, hey, let's look at the weather, let's look at the humidity, let's look at the wind and all of that, conditions. So those are inputs, like your current conditions. And your output is basically, you know, probability of rain, because that's what's gonna, if the probability, if these inputs predict higher probability of rain, you're better off to, if you have the probability of rain is high and the prediction is strong, you're better off taking an umbrella with you. So that's another example of a decision tree. Like, so now we've made it much more concrete, but how do you build such a decision tree, right? We've seen one example for the heart disease, and this is about like, should I carry an umbrella? As simple as that. So the way you build this, and we'll use a specific example called classification regression trees algorithm 23. So the way you do this is you take your data, your input variables, and I have used this as is from StatQuest. So huge kudos to StatQuest. If you want to really go into the details of how to build a decision tree, it's better off to go into that video. But in a sense, you have your input parameters in blue and your output that you're trying to predict in green. And those are your leaf nodes, right? So what you do is you first learn like, hey, what root node do I need to pick, right? Because there are so many of these input parameters. It could be any of these root nodes that you pick. So the way you pick this is by Gini impurity. And you pick the root node that has the highest Gini impurity, right? And so the lowest score of Gini impurity is better, right? So you pick the one that has the lowest score. And by that, Gini impurity is nothing but saying, hey, which of these parameters will have a clean split? Meaning, once you pick that parameter, these two nodes will have a clear direction. From all of these parameters, this parameter has the best split, right? So that's an intuition of finding out like this, you know, it could be popcorn that predicts coolest ice better than soda or age, right? So it finds out that, hey, the impurity of, you know, based on this data that I have, the impurity of love soda is the lowest. And so it's going to pick love soda at the root node. And then iteratively just continue to go through each of these root nodes and build your tree. So identify the root node based on all the parameters that you have, iteratively go through and build the same thing for each of your child nodes, right? And until you get to some stopping criteria, which says, hey, I have got enough you know, purity for these nodes, or I have enough, I don't have enough data to split. So that's how you build a tree, right? Input parameters, output that you're trying to predict. Lowest Gini impurity, recursively add those leaf nodes. Yeah. For more details, StatQuest. I've put a link here. It's also in the slide deck. So the next one, there are two types of decision trees. On the left is a regression tree, and on the right is a classification tree. You see the output is different. On a regression tree, there could be continuous output that you have, and in a classification tree, you would have like, you know, an example is like, hey, is this person going to make a purchase or not? So it's a yes or a no, or a purchaser or non-purchaser. And here you could be like trying to predict engagement, and that's an example of regression tree, right? So I've given you this two examples, but you could build a regression tree or a classification tree based on your needs. There is a problem. Is trees are all good? No, trees are great if with the flexibility that they bring, if you could avoid overfitting, because you could imagine they just encode everything that you have from your training data and then it's overfit, right? So that's a problem as well, because any new data coming in can have a lot of errors, out of sample errors. So how do you deal with this? You add forests. You combine a lot of trees into forests. And so that's where the new algorithm comes in, saying, hey, algorithm 24, random forest. So like we built this one tree, what if we could build several trees? And the way we build those several trees is we bootstrap our original data set and build several new data sets using replacement. So you could reselect those rows and then you do sampling for your data set and you create several bootstrap data sets. In essence, you're creating new data sets, and for every data set that you have from your original input data set, you create this tree. And you have several such trees then, because based on the data set, the tree will be different. And you could build like hundreds of such trees, right? And so once you have built several of these trees, what you're doing is you are reducing overall, you're optimizing for bias and variance, right? Where you say, hey, the sampling is the sampling will average it out, right? And so what happens here is once you have several of these trees, you can average out the result for a prediction across all of your trees. And that's this process of bagging. In bagging, what happens is we use the bootstrapping data set and we aggregate the decision. So we ask this tree, hey, is this person have a heart disease? Hey, is this person have a heart disease? And let's say 4 out of 5 tell you, 5 out of 6 tell you, yes, this person has a heart disease. You take the average, you take the aggregate in some sense. And at some point you can take an average as well. So when you do this process of bagging, you are reducing overall sampling variance that these models would encode lots of this information inside your model if it's just one tree. So you combine and use several trees, you use bagging to find out the final answer, and you check whether this set of trees that you've actually come up with or the number of trees that you are actually using good enough by using out of bag data set error testing. Out of bag data set error testing is basically saying, hey, from all of these bootstrap data sets that you use to build the trees, find out those data sets that are not used in this tree building process, and then check whether you were able to predict accurately for those out of bag or out of those data sets that were not in the bag or not used for building this tree, and check whether you're able to predict accurately. So that's out of bag data set, which can be used for testing whether you have the right accuracy for your model. So then you can adjust the number of trees that you need and the depth of your trees and all of that based on this. But in essence, you get this high level saying you can build a tree, then you can build several trees, and then you can average them or aggregate them based on your requirement and build a random forest. So that's the intuition behind random forest. Empirical Bayesian forest has one more intuition on top of it. It says basically this root node will not change for as many trees as you build even if you take a sample from this large data set, because you might have large data set. That's where empirical Bayesian forest comes in. What you do is it builds on this estimation that, hey, trunk fit or the first few nodes or the root nodes, first few splits can be done with subsamples instead of the full data set, because the intuition is that those, even with the subsamples, you will get the same root splits or the same trunk fit or the same trunk splits, right? And you could imagine that, hey, if you do that, then you could start to parallelize these processing across several machines and do this root child node calculations across several machines, and you might have several parameters that can be computed in parallel. So you could imagine that, hey, for predictive performance, full random forest will have a much higher performance in terms of prediction than this whole empirical, and even better than the subsampling, right? But at the same time, you could start to see that the time complexity and compute complexity would be the opposite, meaning the subsampling can get done faster because you're just working on the subsample. Causal trees are a variation of trees, and so in essence, causal trees, they are optimizing for maximizing the squared difference between the estimated treatment instead of choosing a split that minimizes the impurities. That's the only distinction. So we have trees that are used and are good for prediction, but can we use trees for causal inference? Yes, and that's where causal trees comes in. This is algorithm 26. In a sense, the way you split, or you choose the split by maximizing the square difference between estimated treatment effects. So you see, hey, which one has is maximizing the estimated treatment effect, and that is different than the algorithm we've seen previously, which is to minimize the Gini impurity. So if you do that, then you'll be able to use causal trees to say, hey, what is the causal link here? Finally, semiparametrics and Gaussian process. Some of these things, as you've seen, I've put a this emoji for these previous slides and others, because there are a lot of complexities here. I just want you to get out of the intuition, which is you can build causal trees for causal relationship, not just prediction. And even semiparametrics. There are lots of things here, lots of topics here that can require in-depth 30-minute for each of these topics. So that's why whenever I have slides which have a lot of those, I put a emoji here that you see here, right? So the same thing with semiparametrics, right? Is there a way in which you could take the flexibility that you have with trees, and then you have the restrictions that you have with domain knowledge for the regression models and others? Yes, and that's where semiparametric comes in. It's somewhere in between the linear regression and trees, and we've seen how trees have low bias but high variance, right? And we saw how forests can help reduce those variance and help us with better prediction. Semiparametrics is somewhere in between. It says, hey, I'm going to take the best of linear regressions, which is like, hey, you have some certain domain knowledge, certain ways to encode the distance between two vectors, or like certain parameters that you need. So those are like kernel methods, or ways in which you can encode some information that linear regressions allows you to put, but also continue to maintain some flexibility of the trees and forests. So you think about this as like something in between, like linear regression to one extreme and trees into one other extreme. So there's something in between. And we will learn a lot more about this in chapter 10, which is the last chapter after this one. And there'll be some new concepts as well that we will learn that's not covered in this book after chapter 10, so stay tuned. But in a sense, Gaussian processes, or like support vector machines and gradient boosted machines, there are many ways other than trees that we've not covered in this chapter. This chapter covers only trees and some of those things, and it introduces to this semiparametric something in between, which is what we're going to go in a lot more in detail in chapter 10. So that's it, we're done. So in the comments, I want you to add do you have lots of data in your organization or for your use case? How can you use decision trees? And what's an example that you would wish someone built a decision tree for? I'll give you my one example, and then you can start thinking. What if we could predict cholesterol level, high cholesterol level, from various parameters, like the weight of the person, various other blood markers like HDL, LDL. There's so many parameters. What if you could predict HDL or something, one specific blood marker from various other parameters of this person? How well they're sleeping, what is their stress level, how much exercise are they getting in, and what is their blood markers, what's their weight? That's a good decision tree, right? So add your decision tree in the comments below, and then I'll see you all in the next chapter, which concludes the book, but not our journey. So stay tuned. Thanks.